Now this is Chemistry 3053, and this is the fourth and final video for Chapter 10, which covers radicals. And so here we're going to be considering the radical addition of HBr. That's the anti-Markovnikov addition, which we covered very briefly earlier when we were looking at additions to alkenes and to alkynes. And so now we're going to consider the addition to alkenes here and explain why you get the anti-Markovnikov addition. Then we'll look briefly at radical polymerization, radical processes in the petrochemical industry, although it won't be extensive. It will just be really, a cursory view, and then sort of summarize the reactions in the chapter here at the end, halogenation as a synthetic technique. So this is going to really summarize the entire chapter. So here, radical addition of HBr. Remember, we covered the Markovnikov addition of many different compounds under acidic conditions. And this is just one representative one, Markovnikov addition. Remember, in that step, in Markovnikov addition, the first step, when you have an organic compound in the presence of an acid, the first thing that happens is you protonate the organic compound. And so where does the proton go on this double bond? That's your only functional group, is the double bond. And so it is what is going to be protonated. Where will the proton go? The proton will become attached to the double bond in a manner such that, in other words, which end of the double bond? It will become attached so that you get the more stable carbocation. So the important things to remember here are, first, the first step is protonation. The first step is protonation. And the more stable carbocation is formed. Once you have the more stable carbocation formed, that dictates where Br- must attack. So the regiochemistry of this Markovnikov addition is determined when H plus adds to the double bond. That's the step that determines the regiochemistry, because the Br minus, the bromide, must go to the other carbon. So it's the H plus adding that determines the regiochemistry. Now, you're going to have to keep that in mind as we cover this, because you're going to see the opposite happens when you have a peroxide. This, obviously, you're going to have a radical reaction. But in order to keep you from becoming completely and totally confused, you're going to have to remember what I said up here. Okay, the first step is addition of H plus to the double bond. Okay, that is what happens first. You've got to keep that in mind, because it's the first step that determines the regiochemistry. So let's look at the mechanism of this, and in your mind, keep thinking about what is the first step, because it's the first step, both places, it's the first step that determines the regiochemistry. So here, anti-Markovnikov addition, here we have initiation. Now, initiation is not part of the actual addition. This is just getting it set up to do the addition. So here, go back and look, that reaction, you have a peroxide. So your initiation is the peroxide does a homolytic bond cleavage, because that heteroatom bond is very weak. And so that's where you're going to break. You're going to form two alkoxy radicals. The alkoxy radical is going to react with HBr, and you are generating Br dot. Okay, you have a bromine radical. Now let's go to the actual propagation steps. So now we don't have H plus coming into attack. We have Br dot come into attack. This is a radical addition. And what happens is the Br dot becomes attached to the double bond in a manner such that you generate the more stable radical. So in Markovnikov addition, under acidic conditions, you have H plus adding to the double bond to give you the more stable carbocation. Here we have Br dot adding to the double bond in a manner to give you the more stable radical. So there are similarities in the Markovnikov addition. The more stable cation is formed, and that's at the tertiary position. In anti-Markovnikov addition, the more stable radical is being formed, and that's at the tertiary carbon. But what's different is in Markovnikov addition, the first group that goes on is the proton. Here, the first group that goes on is the Br dot. Okay, and this, since Br dot is going on first and not H plus, this is what causes the reversal in regiochemistry. Bromine is going on first, not second. So you will have this one, the bromine, at the less substituted carbon, not the more stable substituted carbon, because this would give rise to the less stable radical. So the propagation step, Br dot goes on to the double bond. This is the addition step. You have the radical formed at the more stable center, and then that picks up H dot, not a proton, H dot. Okay, and it regenerates Br dot, which goes back up to be one of the reactants in the propagation step. These are the two propagation steps. Okay, notice this generates one of the reactants in the former propagation step. This generates a reactant in the second propagation step. You can also see that you are consuming the reactants and giving the product. Okay. Now, anti-Markovnikov addition. Most of the radicals in solution at any given moment will be the bromine atom. So combination is typically the termination step. Okay, Br dot with Br dot gives you Br2. Okay, and so that anytime you have the two atoms or the two radicals reacting with each other, that gives you the termination step. Okay, so here we have the anti-Markovnikov radical addition of HBr is generally spontaneous. The radical addition of HCl and HI are generally not spontaneous. And so, the addition reactions form a new chirality center here, okay? If the substrate is not chiral, then a racemic mixture will be obtained when one new chirality center is formed. This is very much like we saw with the addition of the ionic addition reactions in Chapter 8. If the starting alkene does contain a stereocenter, then a mixture of diastereomers will be obtained, as before. Now, radical polymerization. Here, when you have ethylene, you get polyethylene. So you are joining together many small units to form a lengthy polymer, depending on how long. Very often N is quite large, in the thousands or hundreds of thousands even. So this is how it happens. So you have homolytic cleavage, of a peroxide to get alkoxy radicals. The alkoxy radical adds to one end of the carbon-carbon double bond, and you get a radical as the product. And then that's the initiation steps. And then that radical attacks another alkene and forms a new radical, which attacks another alkene and forms a new radical, and on and so on and so on. And so it builds up bit by bit to get you a very long polymer. So the propagation steps will take place, thousands or hundreds of thousands of times, and it gives you the overall net reaction, which will be a very lengthy polymer. And so the termination step, there are different termination steps. You can have OR dot react with the alkyl chain radical to give you the alkoxy termination, or you can have two of the alkane radicals couple and just give you a longer reaction. Each of these destroys two radicals and stops the chain reaction. You can also have chain branching, where one of the polymer chain radicals plucks off H dot, and instead of having your radical center at the end of the chain, now you have it in the middle of the chain, and then it reacts with an alkene, so you have the branching. And the highly branched polyethylene forms flexible plastic. The unbranched polyethylene forms more rigid plastic. And so entire courses are built around polymerization. Polymers with varying properties are obtained by polymerizing substituted ethylene derivatives. So you can have propylene, which can polymerize, and then you'll have a methyl group on every other carbon down the chain. Or you can have styrene polymerize, and you'll have polystyrene, where you have a phenyl group on every other carbon down the chain. You can have vinyl chloride polymerize, and you'll have a chloro substituent on every other carbon going down the chain. Or you can have tetrafluoroethylene polymerize, and you'll have every carbon in the chain difluorinated. And so this was Teflon, and it was used initially as a nonstick coating for frying pans. The radical petroleum process, radicals are observed and used and even desired in the petroleum process. So here you can have very long alkanes, and it's desired to fragment those in order to get different products, smaller alkanes that we would be able to use as fuel in our cars or elsewhere. And so there's cracking. Hydrocracking is the same, except it's done in the presence of H2, so that you will form only alkane products, whereas up here you can get alkenes. You can also have reforming, which will, you heat these up and you get fragmentation, and then it recombine to give you branched alkanes. The synthetic utility of halogenation is very great. The chlorination will synthesize alkyl chlorides, except here the chlorination is not specific enough. So you can only really use that. It's only synthetically useful if there's just one chloroalkane product possible. Bromination is slower, it's less energetic, and so it's more selective, and it can be used to create just one product, even though here in this case 1, 2, 3, 4 different products are possible, and yet only one is obtained. So bromination is more useful. The real advantage of halogenation is that you can functionalize what would be an unreactive alkane. Here, this is not a reactive alkane, it's just a hydrocarbon. There's no functional group on this, no place to start a reaction, but you can start one. The halogenation can happen here. And then you can substitute for bromide, you can substitute some other group, or you can form an alkene, and these will take you in many other places. So once you get the halogen, the bromine, on, you can go in many different directions. So this makes something that is not synthetically useful into a molecule that is synthetically very useful. And so here, this is the review of the reactions that you had so far. You've had bromination of alkanes, several chapters ago, using bromine and light. Then you had allylic bromination, also, not several chapters ago, but several sections ago. And this was also in this chapter, but just a few sections ago as well. And here you get only allylic bromination. And then as you just saw a few minutes ago, you can get anti-Markovnikov addition, in which you get the bromine being attached to the less substituted end of the carbon-carbon double bond. And then I just tacked this on. This isn't really added in your book, but I tack this on down here because you may as well have these presented to you together. You remember that it was given to you earlier in the chapter on alkynes. You can have the HBr addition to the alkyne using the peroxide. And once again, you have the bromine substituent going to the less substituted end of the double bond. This is going to the less substituted end. So here the bromine will go to the less substituted end of the triple bond. And so you can see the bromine is going to the terminal carbon, although you do get a mixture of E and Z isomers. And so this page with 1, 2, 3, 4 different reactions, that's really your only summary sheet that you have. And I created this for you that does not have the reagents on here. And so you can print this one off and use it to practice with, where you can have a blank page and write in the reactants to help you study. So this concludes chapter 10.